We have to prove the following statement: 1 plus 3 plus 3 squared all the way until 3 to the power n minus 1 is equal to 3 to the n minus 1 divided by 2. So we're going to write out three statements: P1, Pk, and Pk plus 1. So P1 takes into account when n is equal to 1. So we're talking about the first term only. There are n terms here from the first to the nth term. We're talking about only the first term. So the left side is 1. And the right side, you're going to substitute the n value of 1 into here, into that power. So it's going to be 3 to the 1 minus 1 over 2. And we're not verifying if it's true or not. We're just writing it out for now. P to the k means you're going to substitute the n values that you see in the statement with k. 1 plus 3 plus 3 squared all the way to the nth term, well, in this case kth term, k minus 1 is equal to 3 to the k minus 1 divided by 2. And the pk plus 1 statement will be 1 plus 3 plus 3 squared. So instead of k here, we're going to write k plus 1, right? Because that's the subscript. It's pk plus 1 statement, right? So k plus 1 minus 1. K plus 1 minus 1 is equal to 3 to the k plus 1 minus 1 there. Make sure that you don't write it as a power because it's not a power. The power is out up there, right? Be clear when you write your digits because sometimes it may turn out to look like k plus 1 minus 1 in the power, right? Minus 1 is not the power here. K plus 1 is, right? So divided by 2. So now we're going to show that P1 is true by verifying. So we have to have 1 on the left side. So we have to verify that the right side is also 1. 3 to the first power is 3. 3 minus 1 over 2 is 2 over 2, which is indeed 1. So P1 is verified to be true. The next step is to assume that pk statement is true for arbitrary value k. So for arbitrary k value. Then, if we assume that pk is true, if this statement is true, we can basically formulate our pk plus 1 statement under the same assumption. So we can have 1 plus 3 plus 3 squared. And we're going to write out this term. But we have to have the next statement as well. The next term as well, right? Because pk plus 1 has this term as the last term, right? So that means this term is the one before last in this case for the pk plus 1. So we have to add this term to make it look like the last term on the left side. And on the right side, we're just going to copy this guy over. So 3 to the k plus 1, again power. This is not a power, minus 1 divided by 2. So now what we need to do, we need to compare this statement with this statement. So as you can see, the left side is nearly identical except that from the first to this term, it looks like the left side of the pk statement. However, we have this one unaccounted for. This term is not being present here. So we need to add this on the left side, but also if we add this term on the left side, we will have to add it on the right side. Okay? So we're going to add it on the left side to transform the left side of the pk into pk plus 1. So what we're going to do, we're going to say then 1 plus 3 plus 3 squared. Well, let's indicate this as a pk statement, pk plus 1 statement. 1 plus 3 plus 3 squared plus, okay, up until that. But now we're going to add this term that wasn't there before to make it look like pk plus 1 statement. So I'm going to indicate this in red. So we're adding this guy, and we're setting it to the right side of that pk statement. But since we added it on the left side, we also have to add it on the right side, right? So it's going to be plus 3 to the k plus 1 minus 1, okay? So now our task is to basically show that pk1 k plus 1 statement is true. So we already have the same matching left side here, but we have a different right side. As you can see, we have this and we have this. We have to show that these two guys are equal, right? So in other words, we have to make this side look exactly like this. And then that will show that the pk plus 1 statement is true. All right, so the right side is then what? Let's transform that algebraically. Plus 3, I'm just copying this guy down. We're going to transform this right side to make it look like this side. K plus 1 minus 1. So now what are we going to do? We're going to simplify this guy first, right? So 3 to the k minus 1 over 2 plus 3 to the k, right? That's the next part that you should see. Now the next part is to make this look like a fraction with the same denominator too, right, that this guy has. So that means 3k minus 1 plus, this has to be multiplied by 2 so that it has the same denominator too, right? So it's going to be 2 times 3k, and then the whole thing can be safely divisible by 2, because now this will have a fraction with denominator 2. That's why we combine it under the same denominator. So this is then equal to what? Notice that 3 to the k here has common, it's a common term, right? 3 to the k. So it has coefficients 1, the hidden 1 there, and the 2. So we can combine those. We can put 3 to the k outside, and then we can write 1 plus 2, right? Because 1 is the secret coefficient there, and then the 2 is the coefficient there for the 3 to the k, right? We basically factored out the 3 to the k for these two terms. And then there's a minus 1. Don't forget, there's a minus 1 there still, divided by 2. So this is equal to what? 3 to the so 3 times 3 to the k, right? Because 1 plus 2 is 3. I'm going to put it out in the front. Minus 1 over 2. By exponents, you should already tell this looks like 3 to the 1 times 3 to the k minus 1 over 2, which is equal to what? The same bases, different exponents. That means we can add the exponents under the same base, right? So k plus 1 minus 1 over 2. So bingo. We showed that these two match as we indeed want it, right? We transformed this side to make it look like this with algebraic manipulations, right? So what this means, meaning that we're going to copy the left side now. 1 plus 3 squared plus all the way until 3 to the k minus 1 plus this guy 3 to the k plus 1 minus 1 is equal to this, right? Which we showed was the right side indeed. 3 to the k plus 1 minus 1 divided by 2. Okay? And we say that meaning that the statement holds true, making p to the k plus 1 true, right? Because this whole thing is p to the k plus 1 statement, right? Thus, by the principles of mathematical induction, Pn, the given statement on the top, is automatically proven true, right? Holds true for all n. So I hope this was helpful. Thanks so much for watching. See you in the next video.